So, welcome everybody to ArMOF2021. Just let me adjust the screen. Sorry for that. So, good morning, everybody. Everyone. Good morning, afternoon. Depends on where and when are you watching this. My name is Matias Rasti, and on behalf of the organizing committee, I welcome you to this first Argentinian MOF Symposium. I hope everybody can hear me right, so I will ask my co-organizing committee here present to confirm that audio is doing well, so everybody's hearing me right at the right volume. Okay, perfect. So now ahora en español, para toda la audiencia hispanoparlante que tenemos, que es más o menos el 70% de la gente que se registró. Buenos días, buenas tardes. Bienvenidos al primer congreso de MOF que estamos organizando en Argentina junto con el comité organizador que ahí está compartiendo pantalla con nosotros. Para mí es un gran honor y bueno, un privilegio tener hoy va a acompañar el profesor Shengqian de la Universidad de North Texas y Bianca Provost de Royal Society of Chemistry, que bueno, van a contarnos un poco acerca de las posibilidades editoriales de Royal Society, y el profesor Shengqian nos va a introducir en la temática de MOF y las perspectivas de desarrollo de su grupo y del tema en general. Les cuento que el simposio se va a extender por 3 días a partir del 13 de octubre próximo, durante el 13, el 14 y el 15, en 4 sesiones. Ya van a recibir los que están inscriptos, links a las reuniones en particular. Y bueno, esperamos que todos puedan conectarse y compartir la actividad y participar de las discusiones activamente, ya sea a través de esta plataforma Webex, con el chat que tienen habilitado con preguntas, o también por nuestro canal de YouTube, donde vamos a transmitir las charlas y donde vamos también a recibir preguntas. Now in English, it's my pleasure to introduce Professor Shengqian Ma and Bianca Provost. Professor is doing us a great honor in kicking off this meeting, in which we hope all the community from Argentina will extend the collaboration bonds, and we can have the opportunity to share with you all throughout the world, because we have people signing up from literally more than 67, 70 locations different, and then we hope we can interact with all of you through all of our social media and chat and so in questions after the sessions and everything. So without further ado, I will introduce you to Bianca Provost. She will later on give the space to Professor Shengqian Ma, and I hope everybody can enjoy the session, and we hope we receive interactions from all of you in questions, and we will gladly answer that and forward that to the presenter. So without further ado, now the screen is yours, Bianca. Welcome. Can you unmute your microphone, Bianca?
There we go. Is that working now? Can you hear me now?
Yes, great.
Yes,
we
perfect.
can hear you.
All right. Well, I just want to say, yes, so as Matthias says, my name is Bianca. I'm a deputy editor for scientific journals at the Royal Society of Chemistry, and I'm based in the UK office, so it's afternoon for me now. So at the RSC, I just want to say we're absolutely thrilled to be able to support the first Argentinian symposium on MOFs, and I'm really excited to be able to be here for the kickoff meeting. I'd also just like to take this opportunity to congratulate Matthias and all the organizers on what looks like a really spectacular event, so thank you so much. So before we get started, I'm just going to introduce the 3 journals that are supporting this wonderful event, and the first of which is Molecular Systems Design and Engineering, or MSDE. So this is a journal which was launched in 2016 by the RSC in partnership with the Institution of Chemical Engineers. MSD is an interdisciplinary journal that reports cutting-edge molecular engineering research, and it provides a hub for people really working in this area. exploring molecular systems and their use in understanding applications of technological significance that help to address global challenges. Our international editorial board is led by Juan de Pablo from the University of Chicago, and we're really welcoming of research work on MOFs, whether it's experimental or computational. And in fact, Matthias has a very nice paper on MOFs in a special issue we did on soft materials nanoarchitectonics from a few years ago. So the next journal which is supporting this event is Dalton Transactions, a journal that covers all areas of inorganic chemistry. So that includes organometallic, bioinorganic, materials chemistry of the elements, and includes applications like synthesis, catalysis, energy conversion, storage, electrical devices, medicine. The journal publishes 48 issues a year, and it's led by an international editorial team that includes our editorial board chair, Russell Morris from the University of St. Andrews, and he works on the synthesis and characterization of porous solids. So yeah, journal is very welcoming of MOF research as well. And the journal is actually celebrating its 50th anniversary. So go check out all the cool initiatives they have going on. And finally, last journal is Crystengcom, which is a journal that publishes work on the design and understanding of crystalline materials. So that includes investigation of molecular behavior within crystals, control of nucleation and crystal growth, engineering of crystal structures, and construction of crystalline materials with tunable properties and functions. So again, this is a journal that we'd really love to see any MOF related research, including host guest and multi-component molecular materials. And actually, you'll notice perhaps a name there, Omar Farha, who's very well known in the MOF community, is an editorial board member, in addition to a number of other international expert researchers. So that's it. I'm now very, very delighted to be able to introduce Professor Shengqian Ma, who's, as we've said, is going to be presenting the opening talk for the first Argentinian symposium on MOFs. So just some background on him. After completing a BS degree in Jilin University in China, Professor Ma graduated from Miami University in Ohio with a PhD degree under the supervision of Zhou Zhao, who's currently at Texas A&M in 2008. After finishing a 2-year director's postdoctoral fellowship at Argonne National Lab, he joined the Department of Chemistry at the University of South Florida as an assistant professor in 2010. He was promoted to an associate professor with early tenure in 2015, and then to a full professor in 2018. Last year, he joined the Department of Chemistry at the University of North Texas as the Robert A. Welsh Chair in Chemistry. He's been recognized through a very large number of awards and prizes, so I won't be able to go through all of them. But to name a few, he's received the 2015 USF Faculty Outstanding Research Achievement Award and the 2018 Outstanding Faculty Award. He was awarded an NSF Career Award in 2014, and he's been a Clarivate highly cited researcher every year since 2014. His current research interests are in the development of functional porous materials, including MOFs, COFs, POPs, and microporous carbon materials for energy, biological, and environmental type applications. So with that, I'm just very, very pleased to be able to hand over to Professor Ma so he can give a really exciting sounding talk called Perspectives in MOF Research.
Thank you very much for the nice introduction. Let me show my slides. Oh, can you see the slides? Okay. Can you see the slides, right?
Yep, I can see that. Yes.
Okay, great. Yeah. First of all, I really appreciate the organizing committee to invite me to give this opening talk. It's really my great honor to present for the first Argentina MOF symposium. Since it's the opening talk, I discussed with Matthias about the content of the talk. It's more about the perspective MOF research in the whole community, particularly over the last 20 years. And also I'm going to introduce briefly a small part of my research program. So the title I used, I think I can use the laser pointer, right? I'm not quite familiar with is there a laser pointer somewhere?
I think if you right click on the screen, you can choose a pointer, whatever in the screen.
Yeah. Oh yes, okay, yeah.
There you go. It's user. Oh
okay.
Yeah. No, I think it's
oh,
not
okay.
there.
Okay, sorry. Okay.
Just maybe use the the pointer of the mouse will be great. I mean, we can see it nice.
Okay, great. So the title I use is for my talk today is Nanospace with the Meta-Organic Framework, a Planetarium for Imagination. I hope this can stimulate the young people, particularly in the MOF field, to think about it, for the research in this area. And also we hope can attract more people into this field because, as I said, there are a lot of room for imagination. I think some of you may know Albert Einstein has a very famous quote, is imagination is more important than knowledge. This is particularly important also the case for scientific research. A lot of groundbreaking research is from imagination. Before I go to the content of my research, I'd like to show you a very brief famous preamble of the Star Trek. Some of you probably have watched this.
Space, the final frontier. These are the voyages of the Starship Enterprise. Its continuing mission: to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Okay, yeah, this is a very famous television series, Star Trek. I think still very famous. I watched it before. It's talking about the space travel adventure. Is of course to the other space, universal space. There are a lot of challenges, and also to where human being have never been, and to explore new civilization. And on the other hand, where we're talking about the MOF and porous material, we're going to explore the other end of space. It's the nanospace. So this is a abstract from the Nature review in Nature published by Marky Davis when I was still an undergraduate student back at Jilin University in China in 2002. So you can read Space, the Final Frontier. This preamble to this Star Trek, to capture not only the challenge, in the space travel adventures, but also in the field of nanoporous materials. Means how we can control the size, the shape, and the uniformity of the porous space, and the atom and molecules that define it. Yeah, actually, over the last two decades, almost 2 decades since this paper, right, a lot of challenges in the field, particularly in the MOF field, have been addressed. Now there come a lot of opportunities, I would say enormous opportunity in this field. This is very exciting for newcomers in this field. A brief introduction for the porous materials history. Yeah, porous materials are ubiquitous in nature, and also is closely related to our daily life. Of course, and you guys know the most ancient old porous material, also very useful porous materials, is porous carbons. They've been used since 3,000 years ago from ancient Egypt, and now they are still very important. For example, one of the most important applications for porous carbon material is for water purification, right? For most of the water fountains in the households, including the water filter, they use porous carbons. Of course, the other very important solid state porous materials are zeolites. This we know they are closely related to the oil cracking and a lot of fine chemical catalysis. And then in early 90s, in order to enlarge the pore size of the zeolites for large molecule catalysis, ExxonMobil, they developed the mesoporous silicon material. Now they're being widely used for biomedical applications. Since around late 1990s and early 2000s, they emerged two types of advanced porous material named. One is pure organic, based on covalent bond or hydrogen bonding. It's called porous organic materials, including CMP from Professor Andrew Cooper at University of Liverpool, and the COF, of course, pioneered by Professor Omoyagi, and the porous organic cage also from Professor Andrew Cooper, and the HAFT from Professor Banlin Chen. Of course, the other very important type of material is MOF, is based upon coordination bonds, so all kind of MOF materials. So I think most of you know what MOFs are. They're crystals, very beautiful. You can see they have different colors and different shapes, right? When I introduce the MOF to the high school students when I was back at Florida, I told them they're just precious, porous precious stones, like all kind of gems. So basically MOFs are a hybrid material, we can call it. It's inorganic, organic hybrid materials. They compose, metal ions cluster and organic ligands. It's very easy to synthesize. You use metal ion or metal cluster to link with organic linkers. You can form this framework material. So this is a cartoon to show how the MOF construction. So indeed, MOFs are one of the largest development research field over the last 2 decades. 20 years. You can see the number of publications increase exponentially. So you can always see, and this is I just did survey, asked my students to do the survey. This year is already over 9,000. I think it's 9,000 publications. So a lot of publications. Definitely, it's going to surpass the number from last year. And also, from different countries, China contributes the most in terms of number. As far as I know, probably there are over 1,000 MOF research groups in China. So of course, US is the second. Actually, in US, there are not that many research groups as compared to other countries. Then in India, there are a lot of countries too. I believe, of course, there will be more papers from Argentina in next few years. Currently, we just go in Brazil. This is a very popular research area, and there are a lot of exciting new discoveries in recent few years. So why MOFs are so popular and so hot, right? Or because, of course, they're useful, and also they have some unique features. The most important features, when the MOF was reported back in 1999 by Professor Yag, the MOF5, right? It's extraordinarily high surface area. What does this mean? Currently, the high surface for MOF can, for BET is over 7,000 square meters per gram. So what does this mean? I know Argentina, the most popular game is, of course, football. I'm a soccer, or in the US we call soccer. I'm a soccer fan. Also, Argentina team is actually my favorite team. So, and also I'd like to congratulate Argentina team for winning the Copa America this year. Now, what does this mean? The surface area for 1 gram of the MOF is as large as 2 soccer fields. You can imagine, right? If you put the molecules one by one on the soccer field too, you can imagine how much gas molecules can be stored in the MOF. The second part, unique feature, is the pore size are uniform and can be tuned. You can precisely control the pore size, by just simply expanding the size or elongating the length of the ligand, right? And also the most important feature, of course, because it's a combination of inorganic chemistry and organic chemistry, you can design for various, you can install all kind of function group and tune the topology for all kind of applications. So basically, because of these unique features, high surface area, tunable pore structure, pore size, and also minimal to design, there are a lot of application potentials. So although the pore size or pore space of the MOF is in the nano region, and it can provide us, I said, plenty of room for imagination. And indeed, over the last 20 years, MOFs have been found applications in all kinds of areas. At the early stage, of course, try to mimic zeolites for gas storage and separation. Of course, for carbon capture now, particularly for direct air capture. Of course, for catalysis, also is one of the driving forces for MOF research to mimic zeolites for heterogeneous catalysis and environmental remediation, for toxic gas removal or for some novel agent, degradation and others. So I will spend a few minutes. I think I saw this paper coming out a couple months ago. It's by a number of leaders in this field. They wrote a review article in Underwater Chemistry to summarize the current status of MOF and COF applications. So, and this is the timestone, milestone for the gas applications. For example, the very first one reported by Professor Miyake, MOF1, back in 1995. And the first gas storage, I think, is around 1997, from Suzumu Kitagawa in a paper for high pressure medicine storage in Underwater Chemistry. Then, of course, there are all kinds of gas storage, acetylene storage by Professor Suzumu Kitagawa in Nature, and also for this hydrogen storage in actually the earliest one in 2003 by Professor Miyake. Now they focus on the real engineered and applied for storage, for methane storage. 2018 you can engineer to make it into high density packing, and also to make it into pellet, and also for room temperature hydrogen storage. The other important application then can go to vapor absorption. This is particularly of great significance for some countries lacking water. So for the water vapor absorption and also bracing MOF. Catalysis, as I said, is one of the early driving forces for the MOF research to mimic zeolites. So simply, MOF has a metal can do, of course, loose acid catalysis. This is the very first catalysis paper reported by Makoto Fujita, in 1994 in JAX. I remember, of course, simple loose catalysis and organometallic photocatalysis as a major catalysis. And for the Suzuki coupling and essential, derived material for Fischer-Tropsch reaction, all kind of catalysis can be done in the MOF area. And also for biomedical applications, now I said it's just beyond the chemistry area. The MOF research is now attracts people from chemical engineering and also even biomedical engineering, and the biology people. They can all kind of applications. I want to point out one of the pioneers to develop MOF for bio-related applications is Professor Wenbin Lin now at University of Chicago for MRI, radiotherapy, PET imaging, drug delivery, etc., all kind of photodynamic therapy. And also for sensor, right? You can use for all kind of sensors. So one of the things, of course, for conductive MOF from Professor Dinka, to use for resistor sensor and all kind of sensors. So. And also as a porous material, you can use as solid electrolyte or for proton conductive, and for electrical conductive, and for lithium conductive, etc. All kind of basically related to energy storage. Okay, because so many applications, right? I said it's just a matter of imagination. How bold you can imagine, to use the MOF material for all kind of applications, because I said interdisciplinary chemistry research field combined inorganic chemistry and organic chemistry, the opportunities are unlimited. So of course, because this type of materials are so useful, there are a lot of companies now. Now currently, I think there are 27. The first one is about 2010 they started. There were several famous ones. I think the most famous one for some of is NUMAT in Northwestern. This is one of the most famous MOF startup company. Actually, I'm currently also collaborating with a company at Silicon Valley. We're trying to develop some of the MOF materials to commercialize for some kind of application. Okay, that's from the literature. Now I'd like to take this opportunity to briefly introduce the research program in my group. Actually, Dr. Prof just also briefly mentioned. So the research in my group we focus on the nanospace engineering, basically for all kind of targeted applications. We are doing the MOF, to develop MOF catalysis for small molecule activation. We use the POP for water purification to harvest sources from ocean, from salt lake, and also we use the carbon for fuel cell. Basically, there's three directions in my group. One is MOF. We focus on catalysis, biocatalysis, heterogeneous catalysis. Of course, always doing the gas storage separation. And the POPs, we developed including porous organic polymers and COFs for catalysis and water purification, MOF-derived carbon materials for energy storage and fuel cell. And today I'm going to briefly introduce one topic in my group for the catalysis of MOF application. So catalysis, I think if you noticed yesterday, we were all waiting for. We thought there should be, the Nobel Prize in Chemistry yesterday went to Professor Ben Liss and David McMillan for their contribution. As we made organic catalysis, as always people think, I agree at least, catalysis is the center for chemistry. And the chemistry is the center of our society, right? So catalysis always, so many catalysis Nobel prizes in the past 100 years. Of course, I believe there will come more. We hope, I believe, okay, there will be eventually a Nobel Prize in the MOF area. So sooner or later. And one of the most important applications for catalysis, I said, the early driving forces, one of the early driving forces for the MOF is to mimic zeolites for catalysis, compared with traditional zeolite catalysts and mesoporous materials and other surface catalysts. The MOF catalysis, there's some uniqueness. So one of the things, the MOF, we know the components, right? You have the node, you have the linker, and you also have the you also have the pore space, right? Basically, all these three components can be utilized for catalysis, which is not doable in other types of catalysts, like zeolites. They cannot use organic ligand. There's no organic ligand. Like a surface catalysis, you can only do the surface, right? So, and also you can put the metal in the metallo-organic ligand for catalysis. And for the pore space, of course, you can use to encapsulate all kinds of catalytic species, including enzymes like we developed back in 2010, 2011, and then nanoparticles, all kind of metallic species, all kind of stuff. So, and this is the trend for the publications in the catalysis, MOF catalysis. You can see the number of publications also keep increasing, and then now people, a lot of people, particularly a lot of organic metallic chems in inorganic chemistry field in the States, as far as I know, they are starting to do some MOF using their expertise in the ligand design, organic metallic ligand, to construct the MOF for some very challenging chemical transformation. One thing I like to point, there's no way for MOF to compete with zeolites in terms of oil cracking. Is impossible. We know that because the high temperature, right? But the MOF can become complementary to the zeolites with some kind of catalysis, for example, a lot of fine chemical synthesis. And also MOF can well mimic enzymes, because we know enzymes, right, the most sophisticated catalysts created by nature can catalyze a lot of reactions at very mild condition. Basically, it's ambient temperature, ambient pressure, right? So MOF has potential to mimic enzyme for a lot of catalysis, to lower the reaction conditions. So one of the research topic in my group is for small molecule activation. This has been well studied, I think, over the half century. I would say this topic being small molecule activation to try to mimic the enzyme, to mimic the cofactor. This is particularly a hot topic in organic metallics research area, right? To activate, for example, the most simple, to mimic the oxidase to activate oxygen. Of course, now I have talked to nitrogenase to reduce nitrogen, also carbon dioxide to convert, right, to mimic the photosynthesis system, and the methane oxidation also, and hydrogen. All those small molecules, we know that they can be well activated in nature by enzymes at ambient conditions. So one of the target for my research program is, can we use the MOF to mimic enzyme, can activate those molecules at very mild condition, and for a lot of related chemical transformations. So One of the things I like to start is the hydrogen, hydrogen activation. That's, hydrogenase, right? Enzyme in nature. One of the leading experts is Masita Desberg at Texas A&M. So the hydrogenation, right, basically in nature is a nickel and iron, cluster. They can activate hydrogen at ambient temperature. And also hydrogenation actually is one of the most important reactions in industry. And one of the earliest Nobel Prize in chemistry actually went to hydrogenation. They use transition metal, platinum, rhodium, and palladium for hydrogenation reactions. So, and then later, so I think exactly 20 years ago, okay, yeah, Nobel Prize. Also, asymmetric catalysis went to, precious metal for sharpless meaning. So, with the asymmetric hydrogenation reaction using rhodium and ruthenium-based catalysts. So, went on award a Nobel Prize in 2001. And this year, they don't need to use metal, right? We know that they use organic small molecule for asymmetric catalysis. And so one of the bold thinking for the chemists, can we activate hydrogen? We don't need to use metal, right? Can we just use, pure organic or inorganic species without any metal? This breakthrough came, in 2006 by Douglas Stephan at University of Toronto. He came up with this idea. Phosphorus loose space. We know loose acid, loose space, right? They can combine. And if we increase this step 100 or do not prevent them to combine, they will form a very strong electrical field, right? Look, and can activate hydrogen. This is the groundbreaking research. So, and there are a lot of research, this is a very developed research area, phosphorus loose pair catalysis. And of course, a lot of research over the last 15 years focus on homogeneous. One of the shortcomings for this traditional phosphorus loose pair catalyst, the air sensitive and moisture sensitive, that cannot be regenerated. When we talk about catalysis, so particularly industry, they want the catalyst can be regenerated and recycled. So when we think about, can we use the MOF as platform to combine the phosphorus loose chemistry with the MOF chemistry to hydrogenize this FLP for, so-called precious metal free or metal free. Of course, we cannot claim metal free because MOF has metal, right? We can do at least precious metal free hydrogenation reactions. This is we demonstrated 3 years ago. We successfully encapsulated, the phosphorus FLP, phosphorus loose pair, into the MOF, and to demonstrate it can not only to hydrogenize the FLP and also can, impart some unique, properties for FLP which cannot be achieved for homogeneous FLP system. A brief background for FLP I just mentioned is a loose acid. When you increase the standard 100, they're not going to combine. They're not going to form the bonding. Instead, they're going to form a pair, and there will exist a very strong local electric. The structure can split hydrogen, into hydrogen, a proton and hydride. So, and this process is reversible. So, of course, as I said, there are several mechanisms. I will skip this. 2 electrons, single electron, basically essentially they form the only product. A lot of applications. Phosphorus loose pair is a very popular area. We hope this can get more and more attention. Like this, similar like probably 20 years ago, back in 2000, right? The asymmetric organic catalysis. This is also a new concept. So without any, without really any metal, without even the organic molecule. So they just use the pair. So all kind of applications. The earliest most started is hydrogen activation. Also can be used for carbon dioxide activation, alkane, and for polymers. So as I said, though they have been well developed in homogeneous catalysis area, and of course started to get attention in heterogeneous catalysis. So what we're talking about, how we can, protect and regenerate those, homogeneous catalysts, right? So the idea is we know the MOF, right, have a lot of pore and a lot of function group and open metal side, and the phosphorus loose base is to have a loose base and loose acid. Well, think about it. The base can coordinate one with open metal side. You know, for example, like the amine, right? If we build two amine, you know, like this typical. So what the idea is, well, first to anchor the loose space to the open metal side of the MOF, then use the other terminal base to form the first loose pair, and then they can be anchored, you know, into the MOF space. This is the whole idea. Then we pick this traditional typical and pentafluoro phenylborane. Open metal side chromium. So I will skip this. So first of all, when we load the catalyst, any catalyst in the MOF, there's always a optimal, you know, loading amount. It's not the less the better. It's not the more the better. Always the optimal. We figure out is around 1 millimole per mole per gram that can achieve this, you know, highest, you know, activity. So it uses boron hydride, okay, pinnacle, you know, to do this imine reduction, okay, imine reduction to optimize reaction. And then we expanded the substrate scope, and we found, you know, they can fully catalyze this substrate, this imine compound. And when we enlarge the size, of course, easy to understand, this one is larger than the pore size of MIL-101. They cannot enter the cavity of the MOF, so there's no conversion. But for those three, we found that it's not actually very active. But when we compare with the homogeneous FLP, right, molecular FLP in homogeneous system, they have very good conversion. You can see particularly this one, right? That means it's very interesting. That's a very interesting so-called steric select. Is mainly because we increase the steric hindrance of this imine bond, and in homogeneous, there's no barrier. The FLP, the hydride, can be easily transferred to reduce this one. But that's not the case because of the MOF framework and the structure confinement. The migration of those hydrides is not easy. So that means they cannot easily access this imine bond. That's cause this so-called very interesting steric selective hydrogenation reaction. Of course, this we use the pinnacle, the boron hydride, right? Of course, we want to do the hydrogenation reaction. We also demonstrate we can use hydrogen to reduce this double bond. And also it's comparable or even slightly better than a homogeneous system. That's because of local confinement effect for the MOF, because the substrate concentration and also the reactant in the MOF nanospace is much higher than that's in the homogeneous solution. Of course, one of the beauty for the MOF, of course, the hydrogen catalyst we can easily recycle, regenerate, and also this MIL-101 is very stable. You know, barely the structure can maintain, and also there's barely no slightly drop of the surface. It's mainly because of the loss during the filtration. So, and we're very excited, and also Professor Douglas also is very excited and give us very high comments. As he said, enormous, okay, you know, vast potential for this, you know, the FLP and the MOF, and the opportunity, of course. What he said is, you know, it's enormous, okay. So, and we're very happy, and we demonstrate proof of concept. We can use the MOF, you know, to stabilize and to encapsulate the FLP, and to demonstrate some interesting catalysis which is not observed for homogeneous, like steric selective catalysis, and also the set selective. Can we do something more using the MOF environment, right? The pore environment, because we know the MOF pore environment can be tailored. And can we do some more selective catalysis, like chemoselective, regioselective, of course, asymmetric catalysis, you know, for FLP, asymmetric easy. So, but for chemoselective, for FLP, currently it's very difficult to achieve in homogeneous system. One of the ideas, can we do this, right? When we do the you know, alpha beta unsaturated olefin, right? It's very important for polymer. So the idea is we can tune the, you know, tailor the pore environment. The idea is we can demonstrate we can anchor the FLP. If we can put in another activation, so-called group, in the adjacent area, right, of this anchor port. This can probably to activate one of the preferable to activate, or interact with one of the bond of the alpha beta unsaturated olefin. For example, like this idea is we put the activate, we can preferably to interact with this carbon, carbonyl bond or imine bond, but not the carbon-carbon double bond. Then we can have this chemoselective hydrogenation of this, non-carbon-carbon double bond, right? Then we can use it to make some functional polymer material. Similar, we also use the MIL-101, and the MIL-101 is a very good material. We can purposely to keep some of hydroxyl group and also to control the loading of the FLP and leave some open metal side, because we know open metal side can interact with nitrogen, right? Nitrogen, and also the hydroxyl bond can have the hydrogen bonding with imine group. So then we leave this on purpose and use the FLP. This is a different. We change the FLP, of course, and we demonstrated we want to use the hydrogen bonding hydroxyl group to interact with the imine bond to elongate this imine bond. Then we can select or use the open metal side to interact with the imine bond. So this imine bond will be activated. During the hydrogenation, this imine bond will be selectively reduced, but the carbon-carbon bond will stay. So this is the ideal, if without just use homogeneous, they're going to reduce both, carbon-carbon double bond and the imine bond. And we put in a MOF with an activation group, so they're going to preferably and selective to reduce the imine bond. And as we expected, indeed, when we put this FLP in the MOF with a fraction of hydroxyl group and open metal side, we achieved in the chemoselective, hydrogenation to just reduce the imine bond, but not the carbon-carbon bond. But this is not the case for molecular FLP. They reduce both the carbon-carbon double bond and the imine bond. So this is a very interesting chemoselect because of the tailored microenvironment in the MOF, which is not achievable for homogeneous system. And also we did some calculation, I will skip it, and we found, this interact is exactly like the enzyme, some of the biological system. It's very weak interaction. We just need about 35 less than and 34 kilojoule. For example, the hydrogen bonding with imine bond, right? It's very weak interaction. Also, the open metal side can interact with imine bond, the nitrogen. So we'll elongate the bond and to preferably reduce this imine bond. So this is the mechanism, for FLP, they're going to go to reduce this, and how the hydride they can go to, reduce the imine bond. And also we expand the substrate scope, it can, when we expand it, okay, they all can reduce, the imine bond, but not the carbon-carbon double bond. So this is for hydrogen. Now, of course, we're very excited. Currently, we're still exploring this FLP in the MOF for some more challenging reaction, for example, like CO2. Okay, we're using FLP2 and also for asymmetric, hydrogenation reaction. So besides hydrogen, the small molecule, right, is the smallest molecule in the universe. We know the hydrogen is the lightest one. So how about CO2? CO2 now is extremely hot topic. I think US start to wake up. We know that. I think Europe, okay, has been, dealing with CO2 for a long time. So, and the Paris Agreement, we know that. So, and now the new administration start to wake up and want to put a lot of efforts and investment for CO2. So this is the case, okay. The steady increase of CO2 in the atmosphere, right? And this past July is almost 417, right? We know this, you need to control the temperature within, 0.5 degree and 1.5 degree within the next 5 years and the next 20 years, 10 years. Of course, it's getting warmer and warmer, yeah. And also not only global warming is actually all kind of severe weather. We know what happened this year, right? In Texas, in Dallas, the record low temperature, unprecedented snowstorm, and in Washington, the record high temperature in Germany, the flooding, all kind of, very, very kind of severe weather. So carbon capture, so we cannot eliminate, the fossil fuel, at least in next 25 to 50 years. We still need to use fossil fuel. We just reduce the use, right, the portion. But the sources, of course, we can sequence. There's a lot of research going on. Actually, this started back in Obama administration, It's kind of suspended, during the last administration. So, and instead of storage, of course, actually we can utilize CO2, right? Basically to have this net zero, right, or carbon neutral or carbon negative even, to convert into some value-added chemicals. This nature can do it, right? We know that. The photosynthesis converts CO2 into glucose, right? Of course, it's very complicated. This process also low efficiency, and we can convert CO2 into all kinds of value-added chemicals, right? This is carbon one building block. There are two chemicals actually in this, right? This is one, and the other is carbonate. We can easily use the CO2 to convert. Currently in industry, this one polycarbonate we know is the plastic, right? It's the bottle where you drink everything, right? We can form the polycarbonate. It's very useful for plastic. But in industry currently they use some metal oxide using high temperature and high pressure for this reaction. So as I said, what we can do, we can use the MOF, right? MOF for carbon capture and carbon storage, that's been well demonstrated. When I was even a graduate student, there are a lot of papers for carbon capture. And then now, of course, focus on direct air capture. So how about to convert the CO2 into value-added chemicals, as I just said, right? So this can utilize, you have a lot of CO2, right? Convert the waste into valuable products. So you can basically reduce the cost and even to generate some, a revenue for them to convert into methanol, ethanol, and even some hydrocarbon, and of carbon, even carbon monoxide. So as I said, currently in industry for this additional CO2, they use high temperature, high pressure. As I said, one of our targets is use the MOF, to develop the MOF-based enzyme mimic system, to mimic enzyme. Enzyme can do this kind of reaction at very mild conditions, ambient temperature, ambient pressure. One of the features for enzyme we know, they're polypeptides, right? It's essentially the polymer, and it's flexible and dynamic. Because of this flexibility, they can cooperate. Different active sites, they have the freedom to cooperate with each other. That can, do the reaction at a very mild condition. When we're talking about catalysis, right, essential is reduce the activation energy barrier, right, to speed up the reaction. So it's with the catalyst, the activation energy barrier. Thermodynamically, a lot of reaction is favorable, right? But you want to use kinetically, we need to reduce activation energy barrier. So for traditional catalysts, right, like zeolite and the metal oxide can do this, but need relatively high temperature and high pressure, right? So enzyme, as I said, they're perfect, very sophisticated. They can do these kind of reactions at a very mild condition, right? So reduce this activation energy to a very low level. That's why they can run, catalyze kind of reactions at ambient temperature, ambient pressure. One of the features, of course, is cooperative catalysis. How to design the cooperative catalyst, right? Of course, there are a lot of research going on. We can put some co-catalyst in the pore, in the molecular catalyst, right? In the pore, and incorporate some active site on the pore. But this, the shortcoming, is during the catalysis process, they're going to leach, particularly in solution, right? So, and the other way, a lot of research going on is for surface catalysis. They precisely, place two active sites on the surface and it allows them to cooperate. This is very beautiful chemistry. It's exceptional arts. And if you can achieve, you can definitely get a very high profile publication. Most of them in Nature Science, right? But for surface catalysis, it's not easy to do precise control. So can we learn from nature, right? Nature can do this enzyme. How about we put some, threading some linear polymer like polypeptide enzyme, right? And put some active sites on the the linear polymer and thread in the channel of the MOF or the pore of the MOF. Then they will electrostatic, they can move, right? Cooperate. They can fold and unfold, and they can have this dynamic, like homogeneous catalyst. They can cooperate, with active sites on the pore wall. And this we can achieve the cooperativity, exactly like the enzyme. We need some flexibility, right? Flexibility. So bearing this, we pick this, MIO11. They have the open metal site because the cyclic carbonate is loose acid catalysis. Use some, hydrogen ion, that's cold catalyst. We can thread in this polyionic liquid, right? With the bromide as a cold catalyst. So this is some basic composition. So we pick this reaction. So, cyclization of this epoxide. And then we'll thread in the ionic polymer. We can achieve very high yield. It's much better than the MOF, also better than the physical mixture because MIO11 itself can catalyze a little bit, and it's better, than the physical mixture. So the point is we want to demonstrate that through this host gas operation, how better we can catalyze that. We demonstrate different substrate. So the thing is we want to see how well it can help improve the catalysis, or on the other hand, how low we can lower the activation energy. So then we did the kinetic study at a different temperature for the mixture, and we can see at high temperature the comparable kinetics, but at room temperature this slope is steeper than the physical mixture. That means the cooperativity can help at ambient temperature, like the enzyme. Then we use the Arrhenius equation. That's what you learned in PChem, right? You can deduce to estimate the activation energy, and we estimate at different temperature, and we got, when we thread in the ionic polymer to cooperate with open metal site chromium in the MOF, this can lower the activation energy by 30%, more than 30%. So this is very, very significant. That's why we can catalyze this reaction at ambient temperature. And also the MIO11 we know is a cage MOF, and also we can see using channel MOF, this effect is even more profound. And we did with the PCN333, the channel MOF chromium based, and we can see the kinetics, and the yield is much more profound. And we found, the kinetic constant, when we thread in the ionic polymer in the channel of the MOF, it's almost 3 times, more than 3 times actually, the kinetic constant for the physical mixture. This is much fast, reaction rate, also much low activation energy. So this is a proof of concept. We demonstrate we can use this to mimic the enzyme, right? Use the host gas operation. We can dramatically to lower the activation energy. We use this CO2 cyclization because CO2 now is a very important issue, and also we can easily extend this strategy to other catalysis systems. So besides this, we know that the CO2 chemical conversion, right? In nature, the leaves, we know, right? They use the photosynthesis, right? One of the most important molecule in nature we know is porphyrin, right? In our body system, for oxygen storage, transport, and also for oxidation. And also in nature, in leaves, they have this chlorophyll, right? They can absorb light, then transfer energy to the dark reaction system, right? To through the water oxidation, then produce proton and hydrogen. And through this, there to supply proton and the electron for this CO2 converted into glucose through the Kevin cycle. So essentially, the most difficult reaction for photosynthesis is the water oxidation, actually, right? You have 4 electron transfer. So so-called water oxidation coupled CO2 reduction. That's the current challenge. So what we can do, right? We know titanium is a very good catalyst. Photocathode can reduce CO2 and also can produce hydrogen, right? One of them, but they can do this only under the UV light. Can we learn from nature? We just make a titanium-based MOF within the metal exchange, right? Use the porphyrin as antenna to mimic the lid, to absorb the visible light, and to inject energy to activate, the titanium in this cluster and to become titanium-3. Then we have a cluster, and we can do this water, coupled water oxidation coupled CO2 reduction. Then we did this, and we found we can preferably to reduce CO2 into methane. It's actually very challenging because it's 8 electron transfer. For carbon monoxide, we also see, but the selectivity is very profound. You can see carbon monoxide is really easy because it's 2 electron transfer. And we through this, tune the metal ion exchange, change some of the coning with titanium, we can boost the band gap and also reduce the band gap. And this is some characterizations I will skip. And we did a lot of isotope studies. This is carbon-13 is from CO2. Okay, carbon-13 labeled carbon monoxide, carbon dioxide, sorry. And also we did the oxygen-18 labeled. Okay, we found that produce CO2 oxygen, from water, and also carbon monoxide. So, and even during the duration. So basically, we figure out the mechanism as we expected. Because we have a cluster, here, the titanium, right? We found this titanium-3, indeed, yeah, indeed. When you inject the shine the light, the energy going to go to titanium, to become titanium-3. There are a number of titanium clusters here. They can facilitate this 8 electron transfer, through this water oxidation, process produce proton and hydrogen actually. And through this hydrogen produce CO2 into, methane and carbon monoxide. In addition to the photosynthesis to mimic, right, the artificial photosynthesis using this water oxidation coupled CO2 reduction, right? And also we can use electrocatalysis, right, to supply electricity. Of course, this is much easier because we can use the electricity to directly inject the electron. So, right, this is some of process, using the CO2, the mechanism. Then we also pick the porphyrin. Yeah, the cobalt porphyrin is well known can catalyze CO2. So the cobalt 2 can switch between cobalt 1 and cobalt 3. They can provide 2 electrons. One of the things we need to have a sponge, to allow the electron supply, basically electron sponge, which can, so-called electron vial or electron sponge. So then we put this polyoxymetallate, we know is a electron strand, a lot of electrons. Then we connect to the electrolyte, electrode. They can supply, the electron to the cobalt, and they have some weak interaction with the cobalt. Then we can reduce the CO2 to carbon monoxide. This is a PCN222, and we put the polyoxymetallate in it. And yeah, this is a very beautiful SEM. We can see this tungsten cobalt polyoxymetallate. So, and we did this different loading, and we found we can achieve very high Faraday efficiency over 96 or 98, and the tetra slope is also very small, and it's very selective and reduce CO2 into carbon monoxide. This is some of different loading, high loading, low loading. The high loading, of course, is the best as well, high loading. And Faraday efficiency, the highest one we can reach 98. So, and this is the mechanism I just mentioned. We put this electron sponge in the MOF cavity. They can supply electron, to the cobalt. There's some interaction, very weak interaction. So, and this can, direct the electron transfer and then improve the Faraday efficiency. So, and in addition to photochemical conversion and the photo conversion and the electron reduction, right? So one of the interesting for the MOF, we know we use carboxylate group a lot, right? Actually, if you want to have a free carboxylate in the MOF, it's not easy. I'm not saying it's impossible. So few years ago, I told my students a very bold idea. Can we convert CO2 into carboxylate in the MOF, just to install the CO2 on the pore wall of the MOF, right? If we have the carboxylate group, right, direct from CO2, then we can do a lot of things, right? Actually, I think some of you know, Professor Cisco, he mentioned the most incompatible functional group for the post-synthetic modification called carboxylate, right? The form the bond and as a linker. Also, Professor John Harvey also highlighted, carboxylate-free, very outstanding challenge. So what we are thinking, can we insert the CO2, in the MOF phenol to become a free carboxylate to do something, right, directly in the MOF? Of course, to improve this, we need first to make it feasible in homogeneous system before we can do it. So we pick this system, and we want using this rotative pathway, we can insert CO2 into this phenol, okay. And then we design the MOF ligand, okay, to make this a conium MOF. It's very stable. Then we insert it, the CO2, into this backbone of the MOF. And this is, the UIL 67, and this is after insertion of the CO2. Some characterizations, you can see exactly the same topology. Also, you can see the stretching from the carboxylate group, and the carboxylate is a very weak box acid. We can see from this, TPD study. So, and also then we dissolve, the MOF, digest it, and do the HFPC, and also mass spec. We found there's this carbon-13, there's additional peak is from the carbon, from CO2 formed the carboxylate group. And also we can crystallize the ligand. You can see, right, this is the crystal structure. Okay, we digest the MOF after insertion of CO2. You can see the CO2, the carboxylate formed from CO2 is here. And if you direct use the ligand, you're not going to get the UIL67 because they form the hydrogen bonding. It's going to disrupt the equilibrium for the MOF synthesis. Right? So even with all these results, I think I think that's a few years ago, the review didn't believe we made it. Okay, that's probably several years ago. It's too new and too hard. And then, of course, always as a standard, we need to do the carbon-13 labeling study. Exactly, you can see the peak, right, compared with the previous one. It's much stronger. Very obvious. It's from carbon. This carbon carboxylate is inserted from CO2. Okay, what we can do it? Yeah, this is the mechanism. We insert CO2. We need to do something. We insert the free CO2, the free carboxylate from CO2. What we can do, I say, CO2 is a weak bounded acid. They can catalyze a reaction. This is called methanolysis of epoxide. We demonstrate we can do something a little bit. Then we can catalyze this by using this substrate. It's comparable to the benzoic acid, the conversion yield. And of course, one of the things for this UIO, the conium MOF, there are a lot of defects. You can have the cluster defect, then you will have a free ligand, right, carboxylate. You can also, of course, have the ligand, defects, right? One of the review question is could be due to the carboxylate from the defects. We need to prove, okay. Then we pick a much larger substrate cannot enter the pool. This is what we did. Using this substrate, we can still catalyze using the MOF. There's no reaction, zero yield because they cannot enter because the window size of UIO is pretty small. The cavity is large, right? So, and we found there's no activity, but we use the homogeneous benzoic acid, can still catalyze this substrate. It's comparable to this smaller substrate. That's a strong indication. This carboxylate formed to catalyze this reaction is from CO2 insertion, and also is within the inner pore of the MOF. Of course, the catalyst can be recycled and also very stable. And of course, this is the very first demonstration is to direct CO2 utilization for this heterogeneous state activation in the MOF. Okay, I've talked a lot. I briefly summarize my research which we demonstrate, for catalysis, we can use the FLP, combined FLP chemistry, MOF chemistry for heterogeneous hydrogen activation. Also, MOF can serve as a very diverse platform for CO2 transformation, chemical transformation, photo transformation, electron reduction, and even insertion, etc. And I'd like to conclude my research, my talk. As I said, the space of MOF, can provide you unlimited, room for imagination, and there are endless potentials in this area. It's just a matter of your own imagination, right? When you are a child, you can sleep, you can imagine all kinds. How bold you can imagine, then how well you can create, you can discover in this area. And last, I'd like to thank my group, former group members at USF. I had a big group, over 30 people. And last year, I moved here, my group size shrunk a lot. And at this moment, I want to take this opportunity. If you're interested in PhD studies in the MOF area, you're more than welcome to apply the PhD program at UNT, and more than welcome to join our group. We have plenty of opening positions for PhD students, and also the funding support and collaborators. And thank you very much for your attention. I'd like to answer your question, if any. Thank you.
Thanks a lot, Shengqian, for overwhelming explanation of the whole wide range of topics you and your group are studying. So I was barely able to keep up with the different stuff you presented, but we'll be happy to receive questions from the audience here in the chat or in the YouTube broadcasting. Just for starters, I may have one question that really is something that needs maybe discussing from an experienced researcher as you. So I noticed that when you presented the approach into CO2 capture by using polymer ArMOFs, and then you showed how by using cage type MOF like MIL-101 chromium or channel MOF like PCN, you see some difference between the activity, whether it was one or the other option. My question is more pointed to the fact that if you have a host polymer within the MOF porosity, it's natural that you would lose some of the surface area, right, of the naked MOF, let's say. And since the application of this reaction, or maybe other reactions that you use, are not in gas phase but liquid phase, my question is, how relevant is for a liquid phase based application, let's say separation or liquid phase catalysis or so on, to have a widely activated MOF previous to the experiment? Like some reviewers really argue that you need to have this well-activated MOF, which is okay for nitrogen absorption. But my question is, how relevant it is, this activation process and so on, when you are like aiming for a liquid-based application, in which this might be not as relevant as when you are looking for a gas phase application?
Yes, the particular case we are trying to mimic is to mimic enzyme. We know the enzyme catalysis. I think all of them, I think, are not okay. Maybe a few of them in gas phase. I think probably over 90% of the enzymatic catalysis are in liquid phase. That's why we're trying to mimic, and they have to use the liquid phase because they need to have this adaptability, so-called induced fit, right? You need to have the solution, solvent molecule surrounding. You can have this flexibility to adjust the conformation for the catalysis, and that's why we do this reaction in liquid phase to mimic the enzyme. For the gas phase, I think it's also doable. For gas phase reaction, in principle, it's doable, but this effect we don't know. We haven't investigated. There should be some effect because depending on which reaction you are going to try, I think for the gas phase reaction, the cooperativity, we're not sure because we cannot see this movable, because in gas phase you don't have the solvent. But there should be, you can also introduce this cooperative catalyst in the pore, right? Instead, you're using the small molecule, they're probably going to accumulate at a certain spot in the pore. But for this linear polymer, we can, spread out the active site and also give more accessibility for the substrate to enter. We haven't tested it yet. We haven't done too much the pure gas phase, gas solid phase reaction. I think this is definitely some of the directions was exploring. We don't have this set up in our lab, so that's why we focus on the liquids. I'm pretty sure it's going to work, and particularly for some very challenging reactions. Of course, one thing I like to point out, as I mentioned at the beginning, you cannot go beyond like 300 degrees or 350. Yeah, because there's no way you want to do some reaction like zeolite for oil cracking over 500, 700. No, you know that MOF is going to collapse and or carbonize. So, but below 200 degrees C, I think for some of them like a Mio series and zirconium, they're okay.
Right. Okay. Thanks. And another one that I was thinking you were exposing, whether you show in your slides, when you show these hydrogen reaction catalyzer like FLPs within MOFs, I wonder how it's the reaction carried. Do you have like a solid support for the MOF FLP catalyst, or it's like homogeneously distributed in a colloidal suspension, and then you cycle after cycle you recover?
Some evidence. I skipped. I think I show you. We did the EDS, and also we done the flora and more. When we load, because the distribution of this FLP in the MOF, I think it's very uniform, because it's not like we encapsulate another particle, right? To dope, we use the anchoring. Basically we take advantage of this.
Right.
Yeah, we use this open as we use stabilize. It's different from other people doing. You just throw in the enzyme or another particle or whatever in it. Basically, they are very site specific. Each open med, we don't put all the open med under control. Each loose pair corresponding to one loose acid, and also the control the loading of the open metal side. And I think the current is less than 50%, and you can see the uniformness of those EDS. They're very uniform inside the pore. Also, we have the flora and more. No, it's not. Right. It's not like accumulate at a certain area. No, it's uniformly distributed in the MOF, because this is not a really loading. It's more like a anchor. You have this post-synthetic modification on certain the ligand, right? And the ligand is not going to crowd in one area. No, they did go to the open metal side.
Okay. Thanks. We have some questions in the audience. We have Griselda Narda, which is one of our Perspective speakers later on next week. Okay. And he's thanking you very much for your presentation.
Thank you.
And she has a question. She says, how do you evaluate the efficiency of MOFs compared to other materials capable of capturing CO2 and the specific application, let's say as a device or into a device for like future prospects?
Okay, that's a good question. I think so far, you are talking about direct air capture, right? Direct air capture is now a very hot topic. Currently, there are several types of porous materials being under exploration for direct air capture. One of them, of course, is amine grafted, into the MOF or into some other materials like mesopolysilicon material, etc. That's basically on the chemical absorption to form this bond, carbamate or whatever. So all kind of, you can have very high uptake at a low pressure, but the thing is, the heat absorption is very high. Yeah, typically you will over 90 or even 100, right? Like some of the work reported by Jeff Long and put in the MOF. I think the beauty for the MOF, there's another type of MOF. I think you probably noticed from reported by Professor Marcus O'Rourke, the very famous paper is I participated, so involved. It's a 2013 Nature paper in this inorganic anion as the pillar and very ultra micro pore. Those kind of MOF have extraordinary, CO2 air capture performance, and its heat absorption. The heat absorption is high, but it's not over 100. It's about 50. 50, that's okay. You can regenerate. So compare with its efficiency. You need to consider the uptake capacity. That's one very important, criteria. Also, you need to consider the regeneration. I think overall, at this moment, I think in terms of the overall efficiency, even the capacity is higher than some of the other material. The MOF, we're doing the POP and other material too. They cannot compete with the MOF. So capacity and also the regeneration. I think at this moment, MOF has a lot of advantages, but one of the criticisms always from the community, other communities, okay, is the cost, right? The cost, of course, MOFs are far more expensive than active carbons, than polymers, and then zeolites, and then mesoporous material. But depending on which MOF you're talking about, right? So some of the MOFs actually are very cheap now. Some of the MOF, if you notice, for example, reported by my friend Professor Brandon Chen at UC San Antonio, they can use some natural products, right? The ligand, carboxylate from nature, very cheap, and they're using calcium. Yeah, they can make tons of MOFs at very low cost. I think that the cost issue, of course, if you want to use some fancy ligand, okay, of course, yeah, very expensive. Like for BDC, yeah, like MIO1 actually is damn cheap now, right? You know that. So yeah, depending on which MOF you're talking about, I think it's quite promising, for this direct air capture using the MOF. The cost now, you probably notice there are a lot of companies now, right? Particularly the big leader probably is BASF. They have a big manufacturer in Vietnam and produce 100 kilograms per day, even tons per day of the MOF. So depending on which MOF you're talking about, yeah, some of the fancy MOFs for good publication, right? You are talking about application, probably it's not realistic because too expensive to make the ligand. The major cost for the MOF is the linker, right? If you can get the linker like the BDC, right, very cheap, and some of the linker even cheaper, right? Then this kind of MOFs will have a lot of potential. Actually, some of them actually have been already utilized in industry, like the H-Class1, right? It's already put in some of the trucks. For some other, what's the other question?
Yeah, sorry.
What was the other part of the question he asked?
The other question was like, how do you see these materials? I think I understood this as in the way of applications into a specific device. So it's like to constructing a device or you use an industrial procedure to capture actual.
Yeah, you mean to develop into device? I think this good question. I think the MOF now. Actually, there's some groups doing very beautiful work, right? You can develop deposit the MOF into device, make a very thin film now. I think it's the first step is always to develop the material. The next step, develop into device. I cannot do that, so that's not my expertise. But even I had one PhD student. We can grow very thin, very uniform thin film for the MOF. I did a little bit. So yeah, it's definitely, once you can develop into the thin film, right, that can be used for a lot of applications. Like one of the slides I highlighted is for the sensor application. One of the, like some of the 2D conductive MOF developed by my friend Mutu Dinka, they can make it into device and very stable. And some of them, I think You can make them colloidal, the MOF as to deposit. I think there's a lot of beautiful work from Professor Omar Faha, to deposit some of the MOF nanoparticles or colloidals on the textile to make them into device like a mask for no agent degradation. I think there's another group. I think is at UT University of Dartmouth. I think it's Catherine Moreko. I can't pronounce her last name again. She was doing a lot of beautiful work to making the MOF into device, particularly conducting MOF. It used to be a challenge, a lot of criticism. Now people develop a lot of techniques to, even now you can use the vapor deposition to grow MOF, right? There's some beautiful papers, yes. Yeah. Basically like similar like probably 20, 30 years of work in metallic chemistry. At the beginning, synthesize in the solution, right? Then people develop atomic layer deposition and chemical vapor deposition. Now, chemical vapor deposition is very commonly used now for the metallic species, since compounds synthesis to make some device. I think with the development of technologies and the techniques, right, to make into device shouldn't be a problem for certain MOFs, not all the MOFs, because now they're probably over 100,000 MOF structure or even more. Not every MOF is stable. Only probably about 5% of the MOFs are very stable, can be engineered. And most of the MOFs, they're not stable. We know that. So. But even that, is a lot, right? 5 out of 100,000, 5%, that's a lot. So.
Yes, a lot. Thanks, Professor Ma. And I think one of the members of the organizing committee wants to just go ahead and ask you a question. Is Alejandro there?
Okay.
Yeah, Alejandro.
Please go ahead.
Hello, Professor. Thank you very much. Very exciting talk. Thank you. Thank you. It's a great opening for the symposium.
Thank you.
I was very interested in this incorporation of CO2 as a post-synthetic modification in the organic strats of the MOFs. I was wondering if you can comment a little bit more about the efficiency of this process and which partial pressure are you measuring are you incorporating this CO2 as carboxylates in the linkers?
Yeah. Yeah, we are incorporating the CO2 not as a linker. I think probably you'll see a paper yesterday or the day from yesterday. They also use the CO2 insert into the one of the diamine and to use it as a linker to make the MOF. Right? That's a paper recently published in JACS. That's a very beautiful work. What we did several years ago is different. We want to incorporate the CO2 directly on the backbone. Because the MOF will use a lot of phenylalanine, benzorin ligand, right? We want to incorporate on the benzorin for this so-called carboxylation of sp2 hydrogen, and convert it into free carboxylate. That's what we did. Of course, we need to use some catalyst, no doubt. So this is what we did, incorporate into here. And this is the ligand we put in the benzorin here, and this is the original ligand, the carboxylate, to make them out. This is the carboxylate after insertion. We want to insert the CO2 to become carboxylate for some. This is a very simple demonstration. Okay, we're doing some other application too. Now we not only extend it to the MOF, and we can also extend the system to other parts of material like pulp and cloth. And for some more interesting application, because carboxylate, you can do something, right? For example, you can kill it to some of specific metal ion, right?
Yeah, I'm sorry. My question is rather this is an efficient process or it's only a person.
How efficient is the process for the insertion?
Exactly.
I think this insertion is quite in the homogeneous we can achieve like 95, 90, and then in the heterogeneous system is the packaging we use the catalyst. We can achieve over 75 to 80% conversion.
Nice.
we can control the number of CO2 inserted in the filler. Well, the conversion, of course, is not from CO2. We need to use excess amount of CO2, of course. Yeah, we're talking about for the filtering, so we can control. We had a control. We didn't. We put in the supporting. Yeah, we can. The longer time you put, you can insert more. The shorter time, depending, you can tune. Yeah, you can, convert, 100%. The 100 is difficult, I would say. Okay, at least 75 to 80% of the ligand, with carboxyl is doable. Definitely doable. Yeah.
Great,
And,
thank you.
Actually, I think, this we don't have one of characterization we can see here. Yeah, from here, you can see from the IR, you can see the relative stretch. Yeah, we can control. Yeah, one of the reviewers actually asked us this question. As I said, for the catalysis, you always have a optimal, because you have more active function group, right? You will occupy some of the pore space. That's a trade-off.
Right.
Yeah, we always have an optimal loading, or grafting of the function group, like we did for this phosphate loose pair, also for this neodymium polymer into the MOF. It's not the more the better, because you put a lot of the polymer in the MOF, you're going to block all the pore, Yeah, they're not going to catalyze. Their substance cannot enter. So there's a control. We need to use a certain amount.
Thank you.
Yeah.
Okay. Well, I think we have used the hospitality of Professor Shengqian Ma enough, and we appreciate a lot the time he took for preparing this talk and addressing all the audience and kicking off our symposium, which we hope it will continue over the years, and then sometime maybe we can invite you to visit us in person and let's have some other interesting talks in your future endeavors. And thanks for assisting to everyone. Gracias por asistir a todos los que están ahí en el chat. El video va a estar disponible en YouTube, así que bueno, pueden difundirlo. So, Professor, the video will be available for you to share with among the colleagues and anybody who wants to check out your contribution. And again, thank you very much. Thank you, Bianca, for meeting us, and thank you, the RSC, for your support. And we invite you all to the main events on the next week. On the 13th, we will start, and there will be 4 sessions, so a lot to discuss. And this is already a great token of what we are expecting from all of our speakers. And thank you again, Professor Ma.
Thank you very
Thank
much
you
for the invitation. I look forward to the the main event next week. Thank you. I can't wait to go to Argentina. Yeah, to see to watch one soccer game.
Yeah, we will take you to a soccer game, and then maybe even play with us. We can set up a little match, and then.
Yeah, great.
So thank you very much.
Yeah, thank you. Yeah, goodbye. Thank you very much.
Goodbye, Professor.
Yeah, bye.
So, bye. Bueno, entonces con esto damos por finalizada la sesión. Gracias a todos los participantes del comité organizador por el trabajo arduo en toda esta preparación. Y bueno, a todos los que están ahí en el chat, gracias por participar. Y bueno, los esperamos el próximo miércoles con las sesiones de la mañana. Así que bueno, nada más por ahora y bueno, nos vemos pronto. Hasta luego.